It would be, oh, no, you know, it was for the second house. Like, it's like it's representing the velocities. Yeah.
I just want to go over indeterminate form. So some of the L'Hopital's rule problems that we did yesterday are pretty straightforward, pretty easy. That's what you can expect on the test. Sorry, on the quiz. This indeterminate form, I do want to go over with you, but I'm probably going to revisit it a little bit later and probably include this on another unit's assessment, but not on this one. But I do want to kind of go over these types of problems where it's not as straightforward in terms of L'Hopital's rule. So this is 43. This is from your homework last night. So I want to go over a couple of these just to kind of help you see it. So here, limit as exponent 0 from the right. If I try to plug in 0, I get 0 times 0. It doesn't quite get us to where I want to be. So what we can do is we can kind of be creative in finding ways where we can find a numerator and denominator so we can get kind of create a situation where L'Hopital's rule can apply. So this one here, if I can get a numerator and denominator to show up, but still maintaining the exact same expression, I can put that x squared as 1 over x squared in the denominator, right? Because that's the same thing. I'm forcing a complex fraction so I can get the numerator and denominator to show. And if I plug in 0 from the right, so imagine like 0.1, 0.01, natural log of 0.1, 0.01, that's going to be a positive or a negative infinity. And then if I plug in 0 in for 1 over a really, really small number is also infinity. So basically any infinity or infinity is considered in indeterminate form. So that gives us the green light to do L'Hopital's rule. I can take the derivative of natural log, which is 1 over x. I can take the derivative of negative 2x to x to negative 2, which is negative 2x to negative 3. I can reevaluate and see if it will take me down to a real number. And if it does give me a real number, then I know I found my limit. Yeah.
It's in.
Right. So I think this is more like negative infinity over infinity. So if I think about the natural log graph, if I plug in, let's say 0.00001 in here, I'm going to get a really, really small or a value that is towards that negative infinity range. So I guess technically it's negative infinity over infinity.
Types of problems where you need to know what your graphs look like.
To some extent, yes.
Okay.
Yeah. Mm-hmm. So if we get something where if we try to do direct substitution and it doesn't quite get us something that feels like a real number, then at least for this course, it's the expectation is that how can we involve L'Hopital's rule? They want you to use L'Hopital's rule, so you want to create a situation where L'Hopital's rule can apply. So you want to basically create a fractional expression so that you can hopefully get a 0 over 0 or infinity over infinity to show up so they can go through L'Hopital's rule. Okay. 51, I also want to go over this one here as well. So this one, if I plug in 0, I get 0 raised to the 0 power, and that doesn't feel like anything that is a real number situation. So what we want to do is, remember how we did log differentiation where we knew that a variable raised to variable is difficult to assess. So we want to find a way to bring it down. So here I'm going to take the natural log, or I'm going to let y equal to 2x to the 3x. And I'm not trying to find the derivative per se. I'm just trying to create a situation where I can find a limit easier without that variable sitting above another variable. So if I take the if I step to the side and say, okay, I'm going to let y equal to 2x to 3x, I take the natural log of both sides, and that allows that exponent to come down. I'm not going to worry about this side here. I'm just going to figure out what the limit of this expression is. And if I try to set up using limit, I see that, okay, this is not going to give me anything that feels, because this is 0 times negative infinity, and that is not a real number there. So if we can create a situation where we force that 3x to the denominator, and hopefully it'll give us something that is in indeterminate form, so we can actually use L'Hopital's rule. So here, if I plug in 0 from the right, sorry, this is not actually 0 over 0. This is actually going to be infinity over infinity. Right, so this will give me a negative infinity. This will give me 1 over a really small number, which is really large. So this is indeterminate form, which gives the green light to take the derivative. So I'm going to clean up my numerator and denominator to the point where I can easily find the derivative. Numerator, I can go through u prime over u. Denominator, I can go through chain rule. And once I go through my derivative process, I'm going to clean up and reevaluate and see if that takes me down to a real number. So if I plug in 0 into my end result, it gives me 0. But remember, this is not the answer just yet, because we found the right side of this equation, but the left side still sits that natural log of y. So we say natural log of y is equal to the result of L'Hopital's on the right side, which is 0. And then if I think about, well, natural log of what is equal to 0 is natural log of 1. I can also get this in the exponential form and see that y must be equal to 1. Yeah.
So when you do direct substitution, the very beginning, 0 to 0 is 1. I mean,
oh yeah. So 0 raised to the 0 is considered indeterminate form in its that is unresolved. Yeah.
wait, how did undefined or something? I mean, 0 to the 0 is. We put on the calculator, 0 to 0 is 1.
Right, but
And the answer eventually became 1 as well.
yeah, it did become 1. This is, yeah, let me go back and get back to you. I think this is the process that they want us to learn. So I don't think it's always going to be equal to 1. But yeah, I see what you're saying. 0 to the 0 technically is 1, but these types of problems involve L'Hopital's rule. Okay, so let me get back to you on that. But I'm not going to put this on the quiz, but this is something I'll probably do a more detailed look into this topic probably at the beginning of next semester, since this is technically a BC topic. All right. But the strategy is L'Hopital's rule, because it's not as quick and easy where the numerator denominator are presented to you. You want to create that numerator denominator situation to create a situation where L'Hopital's rule can be applied, but first we got to confirm that L'Hopital's rule stands.
Natural log of 2x approach negative infinity technically approaches 0 right now. Well, natural log of 2x, I forgot how that looks like. And how natural log of x looks like.
So 2 times 0.000001 is going to be like 0.000002. And then natural log of 0.00002 is going to be all the way down here at negative infinity. Because it's going to be really, really close to zero. So if it's close to zero, that y value is going to be really.
Wait, so is it a horizontal shift multiplying the inside of the natural log or?
Well, I'm just plugging in 0 in for x. So if I just think about natural log of, or if I just think of, oh, let's see, are you talking about this part
Yes,
here?
yes.
Right. So natural log of a really, really small number is going to be negative infinity. Right. If I plug in the calculator, I think that should be the case. If I did natural log of 0.0000002, that's going to be a really negative. Here it says negative 20, but if I increase that to, 100 zeros followed by 2, it'd be going towards negative infinity. Okay, but our focus is on these topics that we're working on. Oh, and by the way, I feel like I want to give us just another day, but I don't want to lose a day, so I'm going to push the quiz to Tuesday. Okay. But we are still going to, so we're still going to have 2 days of notes. So tomorrow we'll do EBT. Monday we'll do mean value theorem, but I'm going to squeeze in times for you guys to do review, and then your quiz, 4144 quiz, will be on Tuesday. I will say though that Unit 5 there's a lot of topics condensed into Unit 5, so we got to figure out a way how we can get everything in and still stay on track. Okay, so let me just kind of highlight what we want to be able to do. So being able to do particle motion problem, interpreting from a graph, being able to do L'Hopital's rule, and understanding it's not the same as quotient rule. This is more of a related race problem that sees if we can apply the apply product rule within area formula. So we'll talk about that. We have an extended particle motion problem, which I can go over fully with you. And then linear approximation problem, you'll see one of those. This is a cylinder related race problem. And then on the back, this is a combination problem here. There is Pythagorean theorem, there's area of a triangle, and there's also area or change in degrees or change in theta, rate of change of theta. So I did not put all the different types of related race problem. I think over the course of the notes, the homework, and the AP review, we can get enough practice with all of these. So we want to make sure that we're familiar with Pythagorean theorem problems, area of a right triangle with the 1/2 xy, we got to go to the product rule. Sphere, volume and surface area of sphere, I will provide the formula for that. Yeah, if it shows up on the test. Trig related rates, we've been working on that recently. Cone problems, this is a similar triangle problem, and I will give you a formula for that. Cylinder is easier because the radius can be replaced with a constant, and and it just makes it an easy process. There's no need to go through similar triangles there. And also a similar triangle involving shadow problems. Okay. Formulas to memorize: Pythagorean theorem, area and circumference of a circle, area of a square, area of a triangle, SOHCAHTOA, and everything else I'll give you. I'll give you all the geometric shape formulas. Okay. Yeah, so right now I'm thinking you're probably looking at 3 or so related race problems, and then particle motion, linear approximation, and then a L'Hopital's rule. Okay. So I can say you'll definitely see one of these where it's a combination problem since it hits a lot of things there. And you will see one similar triangle problem. It's either going to be a shadow problem or it's going to be a cone problem. Okay, so just make sure you know how to do. And then I'll put one more problem. That's probably going to be either a sphere problem or a cylinder problem. So I'll give you 3 related rates problems. But hopefully the course between today, tomorrow, Monday, you will get really comfortable with all the different types of related rates. Okay, so let's start with number 1. All right, the figure shows the velocity of a body moving along a coordinate line in meters per second. So this is the velocity function, right? Anything above represents positive velocity. That means these are all places where the particle is moving to the right. Below is wherever the particle is moving to the left. And then if it lands on the axis, that means this is when velocity is what? 0, right? And if it switches from one side to the other, we know that's when it changes direction. Okay, so part A, when is the body reverse direction?
4 to 8.
Yeah, T was 4 and 8 because my velocity changes signs there. Right. When is the body moving at a constant speed? 6 to 7. Yeah, because everywhere else his velocity is either increasing or decreasing. Okay. What is the maximum speed? Yeah, so we have velocity equals 3, velocity equals -3. Those are both equivalent in terms of speed, right? They both are 3 meters per second in terms of speed.
You just take the absolute value.
That's right. Absolute value of velocity is speed. At what time interval is the body slowing down? So speeding up and slowing down, this is where we have to compare what? Velocity and acceleration, right? If one is positive and the other is negative, then we know that speed is decreasing. So okay, let's consider that. So from 2 to 4, we see it's obviously positive velocity because it's above the x-axis, but the acceleration is negative because we know acceleration is the slope of velocity. So yes, we do have opposite signs there. That is where we can expect the particle to be slowing down. Okay, where else do we see opposite signs? 7 to 8, let's consider that. From 7 to 8 is definitely below the x-axis. That's velocity is negative, but it's a positive slope. So we know acceleration is positive. So that's right. One is positive, the other is negative.
What about 6 to 7? I don't know. 0 had to have a sign.
Yeah, so 0, right. So this one is a constant speed. The signs have to be, yeah. So if 1 is 0, then it's not considered. It's not speeding up or slowing down. Yes, holding that constant speed there. Okay, L'Hopital's rule for 2 and 3, and then for number 4, it's asking for the derivative, so it's actually quotient rule, right? Quotient rule for number 4. Okay, try those. just as a side note, and again, I'm not going to take off points if you do this, but on the AP exam, they don't like to see equal signs. So if you're doing L'Hopital's rule, use arrows as much as possible to avoid them looking for ways to take off points for you. But I'm not going to, it's not going to matter for the test. Just want to point that out to you. They don't like to see equal signs for L'Hopital's rule. But yeah, so make sure that before you jump into L'Hopital's rule, that you are actually confirming that we have indeterminate form, right? Because if you get a real number after direct substitution, there's nothing more to do. If you get 10 over 0 or 9 over 0, if the limit doesn't exist, then we don't do L'Hopital's rule, right? We only do L'Hopital's rule if it's 0 over 0 or if it's infinity over infinity. So if you jump to this without first confirming, then that's an issue. Okay, so I'm looking for you to show me direct substitution before you commit to your next step. Okay, so number 5, before we can make any, let me read this problem here. Number 5, sorry, are we okay? 2 to 4. Okay, so number 5, it says, if the length of a rectangle is decreasing at a rate of 2 inches per minute, while its width is increasing at a rate of 2 inches per minute, which of the following must be true about the area of the rectangle? Let's go through this process from a related rate standpoint, right? What's the area of a rectangle? Now, we know that length and width are changing. Everything here is in terms of rates. What information can we gather based off of what's given to us?
DL over D.
Okay, DL over dt is,
Negative 2.
and then what else?
Positive.
Positive. So if we want to involve this, we have to find the derivative. So let's go ahead and find dA dt, but to find dA dt, I have to involve what? Product rule. Okay, so go ahead and build out your derivative, insert these in, and see if you can clean up your derivative into something that will help you decide which of the options to be true. Okay, so see if you can try to make a conclusion as to what could be true about this scenario. So f prime g plus f g prime. Replace -2 for dl dt, replace 2 for dw dt. If I rearrange it and if I factor the 2 out, I get 2 parentheses L minus W. So any conclusion that we make about based off of this, our answer for is easy. What do you guys think? C because why?
Right, so the only time this is positive if my L is greater than W, right? If it's not, then it's gonna be negative, yeah, so, part, answer choice C. Okay, got a full particle motion problem.
But how the equation look like when it's always increasing or always decreasing?
Okay, yeah, so if it's always increasing,
Would it be
Um,
constant?
then, yeah, just be a constant, right?
Okay.
If there's a variable involved, then,
Some
then
condition.
it could be negative.
Okay.
Or if for some reason, if I can have an exponent out here, this is squared for reason, for some reason, then that could also force to a positive all
Yeah.
the time. Okay, hopefully you found, A, B, and C pretty straightforward. Velocity is the derivative of position, and acceleration is the second derivative of position. Plug in 2 and 4 into the appropriate functions. 2 into velocity, 4 into acceleration. Pay attention to your units of measure. And whatever the problem provides you as your units, you're going to incorporate that in your answer. Now, part D, at what time does the particle change direction? We're going to have to start with velocity, set velocity equal to 0, create your velocity sign line, populate your velocity sign line, test your intervals, and then we can read the velocity sign line to help us decide parts D and E. Like, interval where particles moving left, interval where particles moving right, or when the particle changes direction. Okay, so for part D, I set velocity equal to 0. I factored out 3. I continue to trinomial factoring. I got t equals 1, sorry, -1, 3. But I do have a restriction from my original problem. Sometimes particle motion includes negative and positive numbers, but in this case, this particle motion problem is starting at 0 and just moving to the right of 0. So -1 is outside of our domain. We're going to include 3. And then if I want to figure out what direction this particle is moving, I'm just going to use test points. I can choose 1 or 2, any number between 0 and 3, plug into the velocity function and just check the signs. I plug 1 in, I get negative. Negative times positive is negative. Plug in 4, I get a positive times positive, there's a positive. So after I populate the signs, I don't care about the 1 and 4. The 1 and 4 is not going to play a role at all with any interval statement. The whole purpose of the 1 and 4 is just to figure out what the signs are. After that, we don't want to, any statements that you want to make about intervals, you want to use the 0, the 3, and in this case, infinity.
So are you trying to say like if it's, let's just say it's velocity is positive, suddenly it's 0, are you just trying to make sure it doesn't hit that 1 again or like go positive or like, what are you trying to do then?
Oh, you mean with the 1 and 4? Or with what?
Just that whole number line.
Yeah, the whole number line kind of gives me a visual as to what this particle is doing. So we know that when the timer starts, that this particle is going to move to the left for 30 seconds. And then it's going to stop and it's going to turn around and it's going to start moving right 3 to infinity. So because of the plus and minus sign, we can confirm that there's a change in direction at 3 for this particle, because this particle is just going, it's just moving along the number line, just moving either left or right.
Oh, you're just trying to make sure it doesn't go back to the same part of the graph.
No, we just want to see that it actually changes direction.
Oh.
Right. So if the velocity suddenly changes from a negative to a positive or from positive to negative, we just want to know where that occurs. And I can use number line to help me figure that out. Okay, at t equals 0, is the particle moving to the right or to the left? I can just plug 0 into the velocity function from the sign, right? 0 minus 3 is negative, 0 plus 1 is positive, negative times positive is negative. So since v of t is less than 0, I know the particle is moving to the left on that at that moment in time. Okay, what's the formula for average velocity? Change in position over change in time. So we don't touch velocity function there. We use the function above it. Position over time. How do we find displacement?
Final minus initial.
Yeah, final position minus initial position. We don't touch velocity, we just use the position. If we get a negative value, we keep it. If it's positive, then that's fine as well. Now, total distance is related to displacement, but we have to watch out for something with total distance.
is that total distance will be different than displacement if there is a change in what? Change in direction. We have to, and the way that we can figure out if there's a change in direction is we look at our velocity sound line and see between 1 and 4, does this particle actually change direction? It does. We have to kind of track its location at that point where it changed direction, because if it backtracks, we want to count that as a positive value. So we want to include the position at 1, the position at 3, and the position at 4.
Where do you get 3 from?
We got it. Yeah, we got 3 from the velocity sound line, recognizing that there's a change in direction at 3.
Okay.
Now, if there was no change in direction, then your total distance will be the same as your displacement, except for the fact that if it's a negative, you'll turn to a positive. So if there's no change in direction, your distance is not going to be different than your displacement, except for the signs potentially. So we need to find the locations at 1 second, at 3 seconds, and at 4 seconds. But just make sure that we know how to interpret those numbers. We don't want to be adding these numbers together. That's not going to be your total distance. Think of it this way, right? You are on the number line. You are starting at -9. You're walking all the way over to -25, and then you're walking back to -18. Okay, and you're just counting your steps. So from here, you're walking to here, and then from here, you're walking back. Okay, so from -25 to -9, if I subtract those numbers, I can find that distance. I'm taking 16 steps to walk from one point to the next, assuming each step will take me to the next integer value. And then from -25 back to -18, I'm going to take another 7 steps. So if you think in terms of steps, that will help remind you that these numbers will always be positive, and then you can add these numbers together, and that will be your total distance.
So if there was like two places where you like change sign.
Good. So if you have 2 places where there's a change in sign, then you have to include those values as well. So let's say we have x of 1, let's say 2 and 3 both had change in directions, then we got to test 2 and 3, 4, and then there's more back and forth going on.
Okay, so if 2 and 3 change signs, like where would you add?
Right, so let's say x of 1 is 2, x of 2 is -3, x of 3 is 4, and x of 4 is 2. So from 2 to -3, you're walking 5 steps. From -3 to 4, you're walking 7 steps. And from 4 to 2, you're walking 2 steps. So 14. Okay. Yeah, that's okay, is velocity increasing or decreasing at t equals 2? How do we interpret that? Is that talking about velocity? So talk about just acceleration, right? So in other words, is acceleration positive or negative? And then we just look at the sign of acceleration. And you want to make sure that you are justifying with the appropriate words. Anytime I ask you to justify, make sure you don't ever say it is the same sign, or the graph, or that you're specifying. If the speed decreasing, then you want to say velocity and acceleration have opposite signs, right? So make sure when you justify that you are being specific and that you're naming whatever you're referring to. Okay, so this one right here, is the speed increasing or decreasing at t equals 4? You got to compare the signs between velocity and acceleration. Both velocity and acceleration are positive, so therefore speed is increasing, because velocity and acceleration have the same signs at t equals 4. Average velocity is defined as the change in position over change in time. So likewise, average acceleration is the change in velocity over the change in time. Okay. We didn't get through everything on the worksheet, but I think over the course of tomorrow and Monday, we should be able to get through everything. Okay, you guys have a little bit of homework from the end of some AP problems at the end of 4.4 or end of unit 4.
Okay, and then we'll start our next unit tomorrow, first half of class, and we'll continue working on the second half of class. All right, go get your phone.
Yeah, like I know why. This should be doing just this, but like, for actually what is it? Like that's what it's. You get them.